On October 19th, 2025, the European Space Agency issued a statement that made astronomers around the world stop what they were doing and read it twice. The trajectory of 3I Atlas, the interstellar visitor that had captivated observers since July, had changed. Not by much, but measurably, detectably, undeniably. The object that had passed through perihelion 3 weeks earlier was no longer following the path predicted by gravitational models. Something had pushed it off course. At first, this seemed routine. Comets change trajectory all the time. Gas vents from their surfaces as ice turns to vapor, creating tiny rocket engines that nudge them into slightly different orbits. Astronomers have parameters for this, equations that describe how sunlight heats a spinning nucleus and how jets of gas push back. The standard model uses 3 terms called A1, A2, and A3 that capture radial, transverse, and normal acceleration components. Every active comet shows these effects. It would have been stranger if Atlas had not changed course at all. But within hours of the announcement, researchers began checking the numbers, and the numbers did not cooperate. The magnitude of the acceleration was detectable, somewhere between 0.003 and 0.007 meters per second. Small, yes, but large enough to measure with the precision astrometry collected by ground observatories and space telescopes over the previous months. The problem was not the size of the change. The problem was the direction. When a comet vents gas, the force is typically aligned with the sun. Sunlight heats the surface, ice sublimates, gas escapes preferentially from the day side, and the nucleus gets pushed in a predictable direction. Sometimes rotation complicates things, smearing the effect around the spin axis. But statistical averaging over multiple orbits yields a pattern. For Atlas, the expected pattern would have been a small push, mostly in the radial direction, away from the sun, with maybe a transverse component depending on rotation and active area distribution. What ESA reported was neither. The acceleration vector had an oblique orientation that did not match standard outgassing geometry. The initial reaction among planetary scientists was skepticism directed inward. Measurement error seemed likely. Astrometric data gets contaminated by atmospheric distortion, telescope tracking errors, stellar background confusion. Perhaps the orbit determination software had not properly weighted the observations. Perhaps someone had input the wrong reference frame. Teams went back to their data pipelines, reprocessed everything from scratch, applied different statistical filters, cross-referenced positions from multiple observatories. The trajectory deviation survived every check. Then came the second wave of confusion. If this was outgassing, where was the gas? James Webb had characterized the coma extensively before, perihelion, and found carbon dioxide dominating the volatile mix. Everyone expected water to turn on as Atlas approached 1.4 astronomical units from the sun. Thermal models practically guaranteed it. The surface temperature should have crossed the threshold for water-ice sublimation. Observations scheduled for late October were supposed to confirm the transition, to see the carbon dioxide to water ratio drop as buried water ice finally warmed enough to vent. Instead, the ratio barely changed. Carbon dioxide remained dominant. Water stayed quiet. This was the detail that transformed routine into mystery. An acceleration without the expected corresponding activity. A trajectory change without the gas signature that should accompany it. The conservative explanation the one that required the fewest assumptions, suddenly had gaps. If standard cometary outgassing was not producing enough force in the right direction to explain the acceleration, then what was? ESA's statement was carefully worded. It acknowledged three possibilities. First, natural processes not yet fully understood. Second, systematic errors in observation or analysis, despite extensive checking. Third, and this is where the language became precise to the point of caution, dynamics consistent with forces of unknown origin. That third phrase, forces of unknown origin, did not appear in press releases by accident. It was the result of internal debate, revision, legal review. It was the agency's way of saying we see something we cannot explain without speculating beyond our data. Within the astronomy community, the response split along predictable lines. Some researchers doubled down on natural explanations, proposing exotic ice mixtures or subsurface venting geometries. Others began quietly running calculations for alternative scenarios, checking whether rotation state changes or surface property variations could account for the discrepancy. And a small but vocal group started asking the question that had hung over Oumuamua years earlier. The question that respectable scientists are supposed to avoid until all natural options are exhausted. What if this is not entirely natural? What if something about Atlas is responding to its environment in ways that rocks and ice do not? The October surprise was not that Atlas changed course. The October surprise was that nobody could adequately explain why. The change in Atlas's trajectory was not a guess or an approximation. It was measured with the kind of precision that leaves no room for hand-waving. Between October 1st and October 18th, 2025, observatories across 3 continents tracked the object's position against background stars. Each measurement was time-stamped, calibrated, and fed into orbit determination software that had been refining Atlas's path since the summer. When astronomers compared the predicted positions to the actual observations, the discrepancy grew with each passing night. The delta V, the change in velocity, ranged between 0.003 and 0.007 meters per second, depending on which dataset and integration method you trusted. That is 3 to 7 millimeters per second. To put that in perspective, a human walking at a casual pace moves about 1.4 meters per second. Atlas's acceleration was roughly 200 times slower than a leisurely stroll. But in the vacuum of space, over weeks and months, even tiny accelerations accumulate into kilometers of displacement. By mid-October, Atlas was not where it was supposed to be. The offset was small enough that amateur telescopes would not notice, but large enough that professional astrometry flagged it immediately. Orbital elements tell the story in numbers. The semi-major axis shifted. The eccentricity changed by a fraction of a percent. The argument of perihelion, the angle describing where the closest approach to the Sun occurred in the orbital plane, drifted slightly. These are not the kinds of changes you get from measurement noise. These are real dynamical alterations. What made the numbers stranger was the direction. Accelerations from cometary outgassing typically push objects in predictable ways. If gas vents symmetrically from a rotating nucleus, the forces average out over time, and the net effect aligns mostly radially, away from the Sun, with some transverse component depending on spin. If gas vents asymmetrically from active regions, you get more complex patterns, but they still follow rules tied to solar heating and rotation periods. Atlas's acceleration did not follow those rules. The vector, when reconstructed from the orbital changes, pointed in a direction that was neither purely radial nor purely transverse. It had components in both, but the ratio was wrong for standard models. Some researchers described it as oblique, others called it anomalous. A few used the word inconsistent, which in scientific language is a polite way of saying, "This does not make sense." The timing added another layer of strangeness. The acceleration became detectable starting around mid-October, roughly 3 weeks after perihelion. Cometary activity usually peaks at or shortly after closest approach to the Sun, when solar heating is strongest. A delayed response is possible if you have thick insulating layers that take time to heat through, but Atlas had been active for months. The carbon dioxide coma was visible well before perihelion. There was no obvious reason for a sudden change in behavior weeks after the heating maximum. Astronomers ran the numbers again. They checked for software bugs. They tested different gravitational models. They adjusted for relativistic effects, solar radiation pressure, even the tiny pull from Jupiter in the outer solar system. The anomaly remained. Atlas had changed course, and the change did not fit the standard playbook for how interstellar comets are supposed to behave. To understand why Atlas's behavior is strange, you need to understand how normal comets behave. And the textbook example, the object that did everything right, is 2I Borisov. When Borisov passed through the inner solar system in 2019, it was the second confirmed interstellar visitor ever found. Astronomers watched it carefully, and what they saw was comforting in its predictability. Borisov had a visible coma rich in water vapor and carbon monoxide. It showed dust production that ramped up as it approached the Sun and tapered off as it receded. Most importantly, it exhibited non-gravitational acceleration that matched standard cometary models almost perfectly. The acceleration is described using 3 parameters called A1, A2, and A3. A 1 represents the radial component, the push along the line connecting the comet to the Sun. A 2 represents the transverse component, the push perpendicular to the radial direction, but within the orbital plane. A 3 represents the normal component, the push out of the orbital plane. For Borisov, these parameters were small but measurable, and their values fit the expected pattern for a rotating, outgassing nucleus. The forces aligned with solar heating. The magnitude matched the observed coma brightness. Everything made sense. Then there is Oumuamua, 1I, the first interstellar visitor, discovered in 2017, broke the mold. It showed non-gravitational acceleration despite having no visible coma, no detected gas, no dust tail. The acceleration was there in the astrometry, undeniable, but the source was invisible. This sparked years of debate. Some scientists proposed exotic ices, like solid hydrogen or nitrogen, that could sublimate without producing detectable gas. Others suggested that Oumuamua was a fractal aggregate, a fluffy structure with enormous surface area that could vent tiny amounts of gas efficiently. And then there was the hypothesis that generated the most headlines, the idea that Oumuamua might be a light sail, a thin reflective sheet pushed by radiation pressure. The light sail idea was controversial, not because it was physically impossible, but because it required assuming technology where natural processes could still, with some effort, explain the observations. The scientific community largely settled on exotic outgassing as the more parsimonious explanation, though the debate never fully closed. Oumuamua left the solar system before definitive measurements could be made, and it took its secrets with it. Atlas was supposed to be more like Borisov than Oumuamua. It had a visible coma. It showed clear outgassing. Spectroscopy confirmed carbon dioxide and water ice. Every indication suggested this was a normal interstellar comet that would follow normal rules. When the non-gravitational acceleration finally appeared post-perihelion, researchers expected it to fit the standard A1, A2, A3 framework. The coma brightness and gas production rates would correlate with the acceleration. The direction would align with solar heating patterns. The magnitude would match models. None of that happened. The acceleration was there, measurable and real, but it did not behave like Borisov's well-mannered forces. It did not align properly. It did not correlate with activity levels. And unlike Oumuamua, where the lack of a coma made everything mysterious, Atlas had plenty of observable gas and dust. The mystery was not absence of evidence. The mystery was evidence that contradicted expectations. Atlas had a coma, had acceleration, but the two did not connect in the way cometary physics said they should. The predictions were clear and confident. As Atlas approached perihelion at 1.4 astronomical units from the Sun, roughly the distance of Mars's orbit, the surface temperature would cross a critical threshold. Water ice, which had remained frozen and inert during the object's journey through the outer solar system, would begin to sublimate. The carbon dioxide that dominated the coma at 3 astronomical units would give way to water vapor. The mixing ratio, that crucial number describing how much carbon dioxide exists relative to water, would drop. Every thermal model said so. Every precedent from solar system comets supported it. Water was supposed to turn on. It did not happen. James Webb Space Telescope observations, scheduled for late October and early November 2025, were designed to capture this transition. Spectroscopic measurements targeting the 4.3 micron carbon dioxide band and the 2.7 micron water band would track the changing composition as Atlas warmed. Researchers expected to see the carbon dioxide signal weaken and the water signal strengthen. The ratio of 7.6 measured back in August. At 3.3 astronomical units should have fallen to maybe 3 or 4, possibly lower, as water ice deep in the nucleus finally received enough heat to break free. Instead, the ratio barely moved. Post-perihelion spectroscopy showed carbon dioxide still dominating the volatile budget. Water was present, yes, marginally more than before, but nothing like the surge predicted by thermal models. The coma remained stubbornly carbon dioxide, rich even as Atlas passed through the temperature zone where water should have taken over. This was not a small discrepancy. This was a fundamental failure of the models that describe how comets respond to solar heating. Several explanations were proposed immediately. Perhaps the water ice was buried too deep beneath an insulating layer of dust and refractory material. Thermal waves take time to penetrate, and if the mantle was thick enough and thermally resistant enough, water could remain locked beneath the surface, even at perihelion distances. This was plausible, but required a very specific structure. The insulating layer would need to be thick, several meters at least, and composed of material with low thermal conductivity. Observations of the nucleus size and albedo did not strongly support this, but they did not rule it out either. Another possibility was that Atlas simply did not have much water to begin with. Perhaps it formed in a region of its parent planetary system, where carbon dioxide ice was abundant, but water ice was scarce. The carbon dioxide frost line sits farther from a star than the water frost line, so an object forming in the cold outer reaches might preferentially incorporate carbon dioxide. This would make Atlas intrinsically carbon dioxide rich, not just thermally delayed. If true, the water surge was never coming, because the water was never there in large quantities. A third idea involved surface processing over billions of years. Cosmic rays, ultraviolet radiation, and solar wind particles can chemically alter the surface of an object drifting through interstellar space. Water molecules can be broken apart, hydrogen can escape, and what remains gets incorporated into complex organic compounds. Carbon dioxide, being more stable under radiation, might survive preferentially. Over eons, this could create a surface depleted in water, even if the interior retains it. Each explanation had merit. Each required assumptions, but none of them explained why the thermal models, which had worked for countless solar system comets, failed so completely for Atlas. And none of them addressed the deeper question, now taking shape in researchers' minds. If water was not driving the post-perihelion activity, if carbon dioxide was not producing the observed acceleration in the expected way, then what exactly was happening on and around this object? The European Space Agency does not issue statements lightly. Every press release goes through layers of review. Every technical claim gets vetted by multiple scientists. Every word is chosen to balance transparency with caution. So, when ESA published its assessment of the Atlas trajectory anomaly on October 22nd, 2025, the language mattered. The statement acknowledged that the observed acceleration could not be fully explained by standard cometary outgassing models, given the current data. Then it laid out 3 possible scenarios, each with different implications for what comes next. Scenario 1 was natural processes not yet fully characterized. This was the conservative option, the explanation that required the fewest new assumptions. Perhaps Atlas had unusual volatile composition or subsurface structure that produced outgassing patterns different from typical comets. Perhaps the rotation state was more complex than simple spin, involving tumbling or precession that distributed forces in unexpected ways. Perhaps there were localized active regions, geysers or vents on specific parts of the surface that fired intermittently and created asymmetric thrust. All of these were physically plausible. All had precedent in solar system objects, even if the specific combination was unusual. The appeal of Scenario 1 was that it kept Atlas within the boundaries of known physics and known materials. It just required more detailed observations and better models. Scenario 2 was systematic measurement or analysis error. This was the skeptical option, the acknowledgement that even the best instruments and methods can produce artifacts. Astrometric positions depend on precise telescope pointing, accurate star catalogues for reference, and proper correction for atmospheric distortion. Orbital calculations depend on choosing the right gravitational models, the right integration methods, the right statistical weighting of observations. Perhaps the acceleration was not real, but an artifact of how positions were measured, or how orbits were fitted. Perhaps different teams using different datasets would not reproduce the anomaly. The problem with Scenario 2 was that multiple independent groups had already checked the data and confirmed the deviation. Systematic errors that survive cross-validation are rare, though not impossible. Scenario 3 was the phrase that made headlines. Dynamics consistent with forces of unknown origin. This was carefully neutral language that acknowledged a gap between observation and explanation, without speculating about what might fill that gap. Unknown origin did not mean alien. It did not mean artificial. It meant the data showed something happening that current models did not predict, and current observations did not fully constrain. The forces could still be natural, just natural in a way not yet understood or observed in other objects. Inside the European Space Operations Centre, the debates were more candid than the public statement. Scientists argued about how much uncertainty to admit, how much speculation to entertain, how to communicate genuine puzzlement without fueling unfounded claims. Some researchers wanted stronger language, emphasizing that natural explanations were still most likely. Others wanted explicit acknowledgement that the anomaly was significant enough to warrant considering possibilities outside the standard cometary framework. The final statement reflected a compromise, a document designed to inform without alarming, to acknowledge mystery without embracing sensationalism. What the statement did not say was perhaps more revealing than what it did. It did not provide a preferred explanation. It did not offer a timeline for resolution. It did not dismiss any of the 3 scenarios as implausible. And buried in the technical appendix, visible only to those who read past the summary, was a note that ESA had convened an ad hoc working group to coordinate observations and analysis going forward. Working groups get formed when a problem is recognized as both important and unsolved. They are institutional admissions that business as usual is not sufficient. The 3 scenarios were not answers. They were a framework for organizing ignorance, a way of saying we see something, we have checked our work, and we do not yet know what it means. Direction matters. In space, forces do not just have magnitude, they have orientation, and that orientation tells you where the push is coming from. When astronomers reconstructed the acceleration vector for Atlas from the orbital changes, when they calculated not just how much the trajectory had altered, but which way it had been pushed, the result deepened the mystery rather than solving it. The acceleration was not radial. A purely radial acceleration would point directly away from the Sun or directly toward it, aligned with the line connecting the 2 objects. This is what you expect from symmetric outgassing on a rotating comet. Gas vents from the sunlit side, the force averages out over rotations, and the net effect pushes the nucleus away from the Sun. Atlas's acceleration had a radial component, yes, but it was not dominant. The acceleration was not purely transverse either. A transverse acceleration lies perpendicular to the Sun-comet line, but within the orbital plane. This can happen when outgassing is asymmetric due to rotation and active regions that fire preferentially at certain orientations. The rocket effect becomes misaligned with the radial direction, creating a force that speeds up or slows down the orbit, rather than just pushing outward. Atlas had a transverse component too, but again, not in isolation. What Atlas exhibited was an oblique acceleration, a vector that combined radial and transverse components in a ratio that did not match standard cometary models. When researchers ran simulations of rotating nuclei with various active region geometries, they could produce oblique accelerations, but only under very specific conditions. The rotation axis had to be tilted just so. The active regions had to be positioned in particular locations. The venting had to be asymmetric in precise ways, and even then, matching the observed vector required fine-tuning multiple parameters simultaneously. The direction became even more intriguing when translated into galactic coordinates. Atlas was not just moving through the solar system, it was moving through the galaxy with a velocity inherited from its billions of years of wandering. The acceleration vector, when expressed in the galactic reference frame rather than the solar reference frame, pointed in a direction that some researchers found statistically curious. It was not random. It was not aligned with the Sun. It had a component that, if sustained, would alter Atlas's galactic trajectory in a way that moved it toward a specific region of the local stellar neighborhood. This is where interpretation becomes fraught. You can run statistical tests asking what the probability is that a random acceleration would point in that particular direction. The answer depends entirely on your assumptions. If you assume all directions are equally likely, the probability of any specific direction is low. But that does not make the observed direction special, because every direction is equally unlikely. If you assume outgassing should preferentially align with solar heating geometry, then the observed direction becomes more anomalous because it deviates from that expectation. Statistics alone cannot tell you whether the direction is meaningful or coincidental. Some researchers calculated where Atlas would be heading in galactic space if the acceleration continued at the current magnitude and direction for thousands or millions of years. The trajectory did not point toward any particular star in the local catalogue. It did not align with known stellar streams or moving groups. It was simply a direction, one of infinitely many possible directions, notable mainly because it did not fit the easy explanations. Others cautioned against overinterpreting a single vector measured over a few weeks. Cometary activity is variable. Jets turn on and off. Rotation states evolve. The acceleration observed in October might not persist into November or December. Projecting a short-term deviation into a long-term trajectory was premature. But the unease remained. The vector was oblique when it should have been simpler. It pointed somewhere when it could have pointed anywhere. And the more researchers tried to fit it into standard models, the more parameters they had to adjust, the more special conditions they had to invoke, until the explanation started feeling less like physics and more like storytelling. Within days of the ESA announcement, mission planning teams at space agencies around the world began running calculations. Not official proposals, not funded studies, just quiet spreadsheet work done by engineers and scientists asking the same question. Could we reach it? Could we send a spacecraft to Atlas before it leaves the solar system forever and disappears back into interstellar space? The answer depended entirely on how fast you could move. Atlas was already outbound. Perihelion had passed in late October 2025, and the object was now climbing back out of the Sun's gravity well, picking up speed as it headed toward the outer solar system. Every day that passed added distance, added velocity, made an intercept harder. The window was not measured in years. It was measured in months, perhaps 18 at the outside, before Atlas would be too far and moving too fast for any realistic mission to catch up. The Hera spacecraft, currently on its way to the Didymos binary asteroid system, came up in conversations. Hera was a European mission launched in 2024, designed to study the aftermath of NASA's DART impact. It had ion propulsion, decent delta-V capacity, and it was already in space. Could it be retargeted? The orbital mechanics said no. Hera's trajectory was committed. The fuel budget was allocated. Redirecting to Atlas would require a velocity change far beyond what the spacecraft could provide. And even if it could, the diversion would sacrifice the Didymos science entirely. Hera was not an option. JAXA, the Japan Aerospace Exploration Agency, had experience with asteroid sample return through the Hayabusa missions. Internal feasibility studies began circulating, exploring whether a Hayabusa 3 mission could be fast-tracked and aimed at Atlas instead of a near-Earth asteroid. The engineering was plausible, but the timeline was brutal. Designing, building, and launching a spacecraft capable of intercepting an interstellar object moving at 58 kilometers per second relative to the Sun would take years under normal circumstances. Compressed schedules might cut that to 3 years, maybe 2, if corners were cut and risks accepted. But 2 years was too long. Atlas would be gone. NASA convened what it called a Rapid Response Assessment Team, a group tasked with evaluating whether any existing mission in development could be adapted or whether a new dedicated mission could be conceived, funded, and executed in time. The constraints were unforgiving. Launch opportunities depended on planetary alignments. Jupiter gravity assists, which could boost a spacecraft's speed significantly, were only available during specific windows. The next favorable geometry was not for another 16 months. A direct trajectory without gravity assists would require enormous fuel, enormous rockets, and enormous cost. The numbers kept coming back negative. A flyby mission, the simplest option, would require at least 3 years from approval to launch under optimistic assumptions. A rendezvous mission, one that matched speed with Atlas and stayed alongside it, was out of the question entirely. The delta V required to catch up and then slow down relative to an object moving that fast was beyond current propulsion technology, unless you were willing to spend a decade in transit. And a decade was 9 years too long. Private interests began making noise. Companies that had been talking about asteroid mining and deep space ventures saw an opportunity for publicity, if nothing else. Proposals appeared online, some serious, most aspirational, a few outright fantasy. Build a CubeSat with a solar sail. Launch it on a commercial rocket. Let radiation pressure accelerate it slowly over years. The math did not work, but the enthusiasm was real. By mid-November, the conclusion was unavoidable. No mission would reach Atlas. The object had appeared, behaved strangely, and would leave without humanity ever touching it, sampling it, or observing it up close. The most we could do was watch from a distance and hope the telescopes captured enough data before Atlas faded from view. The mission clock had not just started. It had started and already run out. Light curves tell stories. When you measure how bright an object appears over time, when you track the peaks and dips as it rotates, and different surface areas catch the sunlight, you learn about its shape, its spin, its stability. For asteroids and comets, light curves are usually periodic. A blob tumbles through space with a predictable rhythm. Every rotation brings back the same pattern. Bright when the broadside faces you, dim when the narrow end points your way, over and over in a regular cycle. Atlas did not cooperate. Photometric observations collected through October and November 2025 showed brightness variations that refused to settle into a clean period. Early data suggested something around 8 to 12 hours, but as more measurements accumulated, the pattern became irregular, the peaks did not come back at consistent intervals. The amplitude, the difference between brightest and dimmest, changed from one rotation to the next. This was not the signature of a simple tumbling rock. This was non-principal axis rotation, the kind of chaotic motion you get when an object spins around an axis that is not aligned with its moment of inertia. Imagine throwing a football in a smooth spiral versus tossing a brick end over end while it also wobbles side to side. The football has stable rotation around its long axis. The brick, if you throw it wrong, tumbles chaotically. Atlas was tumbling. The rotation was complex, possibly involving precession, where the spin axis itself slowly circles around another axis, or nutation, where the spin wobbles like a failing top. Disentangling these motions from ground-based photometry, where you are watching a faint, fuzzy object through a turbulent atmosphere, is extremely difficult. The comparison to Oumuamua was immediate and uncomfortable. Oumuamua also showed non-principal axis rotation. Its light curve had a dramatic variation, brightening and dimming by a factor of 10, implying an elongated shape tumbling chaotically. Some models suggested Oumuamua was cigar-shaped. Others preferred a pancake or disc geometry. The chaotic spin was cited as evidence for either a natural fragmented structure or, in more speculative proposals, an artificial geometry, like a light sail tumbling after its guidance system failed. For Atlas, the chaotic rotation raised questions about internal structure. Objects with uniform density and regular shapes tend to settle into stable spins over time. Energy dissipation from tidal flexing or internal friction damps out wobbles and leaves the object rotating smoothly around its most stable axis. If Atlas was still tumbling chaotically after billions of years in space, that suggested either recent disturbance or non-uniform mass distribution. Maybe the interior was not solid. Maybe it was a rubble pile, a collection of fragments loosely held together by gravity with voids and irregularities that prevented stable spin. Or maybe something had happened recently, a structural shift or impact or outgassing event that imparted angular momentum and kicked the rotation into chaos. The timing was suspicious. Atlas had been observable since July, but detailed light curve monitoring only ramped up in September and October. There was no baseline from earlier epochs to confirm whether the rotation had always been chaotic or whether it had changed. If the tumbling was new, if it started around the same time as the trajectory anomaly, that would suggest a connection. Perhaps whatever caused the acceleration also disturbed the spin state. Attempts to model the rotation ran into the same problem as every other aspect of Atlas. You could fit the light curve with specific assumptions about shape, albedo variation, and spin dynamics. But the solutions were not unique. Multiple combinations of parameters could produce similar photometric signatures. Without resolved imaging, without actually seeing the shape of the nucleus, the light curve data alone could not distinguish between a chaotic natural tumbler and something with a more organized structure rotating in an unusual way. The rotation was a riddle wrapped inside the larger mystery, another piece of Atlas that refused to behave according to expectations. Hubble Space Telescope pointed at Atlas again in early November 2025, this time with a specific goal. Not spectroscopy, not nucleus size limits, but imaging. High-resolution imaging designed to map the structure of the coma, to see where the dust was coming from and where it was going. What came back from the cameras was both expected and deeply puzzling. The coma was asymmetric. This alone was not surprising. Comets almost always show asymmetry because solar heating is directional, and rotation creates preferential venting from active regions. You expect the coma to be brighter on the sunward side, where fresh ice is sublimating, and fainter on the anti-sunward side, where gas and dust drift away into the tail. Atlas followed this pattern, but only partially. Enhanced brightness appeared on the sunward hemisphere, exactly where solar heating should drive the strongest activity. But there were also secondary plumes, fainter extensions of dust that emerged from regions not directly facing the sun. One plume extended roughly perpendicular to the Sun-comet line. Another appeared at an oblique angle. These were not diffuse halos. These were directional jets, collimated streams of dust being ejected from specific locations on the nuclear surface. Jet activity from discrete vents is common in solar system comets. Observations of Comet 9P. Tempel 1 during the Deep Impact mission showed multiple jets firing from small active areas, while most of the surface remained inert. The jets on Atlas were similar in appearance, but strange in their geometry. When researchers tried to correlate the jet directions with the expected rotation axis and solar illumination angles, the alignment did not work. The jets were firing from locations that should have been in shadow, or at angles that did not match simple solar-driven sublimation. Here is where the asymmetry became a problem for explaining the trajectory anomaly. If the acceleration was caused by outgassing, the direction of the acceleration should align with the direction of maximum gas and dust release. Momentum is conserved. Gas leaves the surface in one direction. The nucleus recoils in the opposite direction. The jets visible in the Hubble images were releasing dust, and where there is dust, there is gas driving it. But when astronomers calculated the net thrust that would result from the observed jet directions and estimated mass loss rates, the vector did not match the acceleration measured from orbital changes. The main sunward plume should have produced a force pushing Atlas away from the Sun, mostly radially outward. The secondary plumes, depending on their timing and intensity, could add transverse or oblique components. But the combination did not reproduce the observed acceleration vector. Either the visible dust plumes were not the dominant source of thrust, or there was additional outgassing happening that was not producing visible dust, or the relationship between dust emission and momentum transfer was more complicated than standard models assumed. One possibility was that the dust and gas were decoupling. In typical cometary outgassing, gas molecules drag dust grains along as they escape. The gas is invisible in optical images, but the dust scatters sunlight and reveals the jet structure. If Atlas had gas venting strongly from regions that produced little dust, perhaps due to grain size distribution or surface composition, those jets would be invisible to Hubble, but still capable of generating thrust. The acceleration would then come from invisible jets, while the visible plumes were secondary features, not representative of the total outgassing. Another possibility was time variability. The Hubble images captured a snapshot, a moment in time. If the jet activity changed as Atlas rotated, if different vents turned on and off over the course of hours or days, the integrated momentum transfer over weeks could differ significantly from what any single image suggested. Matching the acceleration would require knowing the full duty cycle of every active region, information that snapshots could not provide. The dust plumes were there, visible and real, but they pointed in directions that deepened the confusion rather than resolving it. Solar Orbiter was was not looking for Atlas. The spacecraft, launched by ESA in 2020 to study the Sun up close, was focused on its primary mission, mapping solar wind dynamics and the Sun's magnetic environment. But space is big, and trajectories cross in unexpected ways. In late October 2025, Solar Orbiter happened to pass within roughly 0.2 astronomical units of Atlas's position, close enough that the spacecraft's plasma instruments could sample the space around the interstellar visitor, even though Atlas itself was far outside the field of view. The data came down in early November during a routine telemetry pass. Engineers processing the plasma measurements noticed something odd in the magnetic field readings. There was a localized disturbance, a small deviation from the background interplanetary magnetic field carried by the solar wind. The disturbance was weak, barely above the noise threshold, but it was there, and its timing coincided with Solar Orbiter's closest approach to Atlas's calculated position. Magnetic disturbances around comets are not unusual. When a comet releases gas, that gas becomes ionized by solar ultraviolet radiation. Charged particles, ions and electrons interact with the magnetic field embedded in the solar wind. The interaction creates what is called an induced magnetosphere, a region where the interplanetary field gets draped around the comet and distorted. The effect is well understood. Missions to comets like 67P, Churyumov-Gerasimenko have mapped these induced magnetospheres in detail. What made the Solar Orbiter detection strange was the strength and structure. Atlas was at 2.1 astronomical units from the Sun at the time of the measurement, active but not dramatically so based on ground observations of coma brightness. The expected magnetic signature for a comet of that size and activity level should have been subtle, a gentle bend in the field lines. What Solar Orbiter detected was sharper, more localized, almost as if there was a discrete source rather than a diffuse cloud of ionized gas. One straightforward explanation is that Solar Orbiter caught Atlas during a sudden outburst. Comets occasionally have eruptions where subsurface pressure builds and then releases violently, producing a temporary surge in gas and dust production. If Atlas had an outburst coinciding with the flyby, the ionization and plasma density would spike, creating a stronger magnetic signature. Ground-based observers did report a slight brightening of the coma around the same time, though the photometry was not conclusive due to weather and scheduling gaps. An outburst fits the data, but requires fortuitous timing. Another explanation involves the structure of the coma itself. If the outgassing was highly collimated, concentrated into narrow jets rather than spread over a broad region, the plasma density along those jets could be higher than models assume. A jet oriented towards Solar Orbiter would create a localized magnetic disturbance, even if the total gas production was modest. This also fits, but requires specific geometry. Then there is the possibility, remote but discussed in internal ESA communications, that the magnetic signature was not induced but intrinsic. Objects generally do not generate their own magnetic fields unless they have metallic cores with dynamo activity or remnant magnetization from ancient magnetic environments. Atlas is thought to be a small icy body, not a differentiated planet. But if it contained ferromagnetic materials, iron-nickel grains mixed into the structure, and if those materials had been magnetized at some point in the past, the object could carry a weak residual field. Solar wind interaction with an intrinsic field would produce a different signature than interaction with ionized gas alone. The detection was a single data point from one spacecraft passing nearby. It was not repeated. It could not be confirmed independently. But it added another layer to the growing list of things about Atlas that did not quite fit expectations. The magnetic disturbance was there in the data, weak but real, hinting at something in or around the object that interacted with the solar wind in ways standard cometry models did not fully predict. Mass and volume should tell you density, and density tells you what something is made of. Ice has a density around 0.9 grams per cubic centimeter. Rock ranges from 2.5 to 3.5. Iron is 7.8. Measure the mass, measure the size, divide one by the other, and you know whether you are looking at a snowball, a boulder, or a chunk of metal. For Atlas, this simple calculation produced a result that made no physical sense. The mass estimate came from the acceleration. When a force acts on an object, the object accelerates according to Newton's second law. Force equals mass times acceleration. If you know the force, which you can estimate from the observed outgassing and coma brightness, and you measure the acceleration from orbit changes, you can solve for mass. The calculations were uncertain because the force estimate depended on assumptions about gas production rates and particle velocities. But they converged on a range. Atlas had a mass somewhere between 10 to the 11 and 10 to the 12 kilograms, roughly 100 million to a billion metric tons. The volume estimate came from Hubble's upper limit on nucleus size. The brightness of the central condensation, the unresolved core of the coma, constrained how large the solid body could be. Hubble set an upper limit of about 5.6 kilometers in diameter, assuming a reasonable albedo. If you take that size and calculate the volume of a sphere, you get roughly 90 cubic kilometers. Even if Atlas was not spherical, even if it was elongated or irregular, the volume was on that order of magnitude. Divide the mass by the volume, and you get density. For Atlas, depending on which end of the mass range and size range you picked, the density came out somewhere between 0.1 and 0.5 grams per cubic centimeter. That is less dense than water ice. That is less dense than snow. That is approaching the density of aerogel, the ultralight synthetic foam used in spacecraft insulation. No natural solar system object has bulk density that low unless it is a loosely bound rubble pile with enormous voids. Rubble pile structures are real. Many asteroids are gravitationally bound, collections of fragments, with porosity exceeding 50%. But even rubble piles have limits. Gravity has to hold the pieces together. If the density is too low, if the voids are too large, the structure becomes mechanically unstable. Self-gravity at the scale of a 5-kilometer object is weak. Any significant spin or tidal stress would pull a highly porous rubble pile apart. Atlas was tumbling chaotically and had survived perihelion passage, where solar tides are strongest. A density of 0.2 grams per cubic centimeter did not seem consistent with structural survival. The alternative was that one of the inputs was wrong. Maybe the mass estimate was too high. If the outgassing force was weaker than assumed, if the gas was moving slower, or the production rate was lower, the inferred mass would drop. That would raise the density into a more reasonable range. But the coma brightness and spectroscopic measurements constrained the gas production fairly well. Cutting the mass estimate in half required assumptions about outgassing efficiency that contradicted observations. Or maybe the size estimate was wrong. If the nucleus was smaller than Hubble's upper limit, say 2 or 3 kilometers instead of 5, the volume would drop and the density would rise. A 2-kilometer diameter nucleus with the same mass would have density closer to 1 gram per cubic centimeter, icy but plausible. But fitting a smaller nucleus into the Hubble photometry required higher albedo or unusual scattering properties, and both of those conflicted with the red color and polarization data. The density problem had no clean solution. Either Atlas was implausibly fluffy, or the mass estimate was wrong, or the size estimate was wrong, or the relationship between outgassing and acceleration was more complicated than the models assumed. Each escape route required discarding or reinterpreting data that seemed solid. The object was there, real and measurable, but the measurements refused to assemble into a coherent picture of what it was made of. Isotopes are nature's fingerprints. Atoms of the same element can have different numbers of neutrons, creating variants with slightly different masses. Hydrogen usually has 1 proton and no neutrons, but deuterium has 1 proton and 1 neutron. Carbon is usually carbon-12, 6 protons and 6 neutrons, but carbon-13 has an extra neutron. The ratio of these isotopes in a material tells you about the conditions when that material formed. Temperature, pressure, chemical environment, all of these leave traces in isotope ratios. In November 2025, a team using the high-resolution spectrograph mode on James Webb managed to capture a spectrum of Atlas's coma with signal-to-noise good enough to attempt isotope measurements. Specifically, they targeted deuterium to hydrogen, the D to H ratio, in water vapor. This is one of the most important measurements you can make for understanding where an icy object formed. Water in the solar system has a D to H ratio of about 150 parts per million. That is the standard, set by the composition of Earth's oceans and found in most inner solar system materials. Comets from the Oort cloud, the distant reservoir of icy bodies far beyond Neptune, tend to have higher D to H ratios, sometimes 2 or 3 times the standard value. The reason is temperature. Deuterium preferentially gets incorporated into ice when water condenses at very low temperatures, below about 30 Kelvin. The colder the formation environment, the more deuterium ends up in the ice. The preliminary measurement for Atlas came back at approximately 210 parts per million, plus or minus 40. The error bars were large because the spectral lines were faint, and extracting deuterated water signal from the noise was difficult. But the central value was elevated relative to standard solar system water. Not wildly elevated, not 3 or 4 times the terrestrial ratio, but high enough to be noticed. The statistical significance was about 3.2 sigma, meaning there was roughly a 1 in 1,000 chance that the measurement was a random fluctuation, and the true ratio was actually standard. 3.2 sigma is tantalizing, but not definitive. In particle physics, 5 sigma is the threshold for claiming a discovery. In astronomy, standards are looser, but 3 sigma results are treated with caution. They suggest something interesting, but do not prove it. The elevated D to H ratio, if real, implied that Atlas formed in a cold environment, colder than the region where most solar system comets originated. That was consistent with the object's interstellar nature. A planetary system around a different star might have different temperature gradients, different snow lines, different deuterium fractionation. The team also attempted carbon 13 to carbon-12 measurements in carbon dioxide, but the signal was weaker and the uncertainties larger. The ratio appeared marginally non-solar, shifted toward slightly higher carbon-13, but the error bars overlapped with the solar value. No strong conclusion could be drawn. What made the isotope results frustrating was their inconclusiveness. If the D to H ratio had been 400 parts per million, wildly above anything seen in the solar system, it would have been a clear signature of exotic origin. If it had been 150 exactly, matching solar system standards, it would have suggested Atlas was chemically similar to local comets despite its interstellar trajectory. Instead, it sat in the grey zone, elevated enough to hint at difference, but not elevated enough to scream it. Follow-up observations were planned for December, when Atlas would still be bright enough for high-resolution spectroscopy. The goal was to reduce the error bars, push the significance above 4 sigma, and measure additional isotope systems, like oxygen-18 to oxygen-16 and nitrogen-15 to nitrogen-14. Each ratio probes a different aspect of formation chemistry. Together, they could build a profile of the environment where Atlas originated. But December observations depended on telescope scheduling, weather, and whether Atlas remained active enough to produce detectable gas lines. Isotopes whisper, they do not shout, and sometimes, by the time you build the instruments sensitive enough to hear the whisper clearly, the source has already moved out of range. When something behaves strangely, the first instinct is to check whether anything else has behaved the same way. Astronomers have been watching comets for centuries. Thousands of observations, hundreds of well-characterized objects, a deep archive of photometry, spectroscopy, and orbital data. If Atlas was exhibiting unusual but natural behavior, perhaps some solar system comet had done something similar. Finding a precedent would not explain Atlas completely, but it would provide a framework, a proof that nature could produce this kind of anomaly without invoking anything exotic. The search began with Comet 29P Schwarzmann-Wachmann 1, an object famous for its unpredictable outbursts. 29P orbits between Jupiter and Saturn, far enough from the Sun that it should be cold and inert. Instead, it erupts periodically, brightening by factors of 100 or more over the course of days or weeks, before fading back to quiescence. The outbursts are thought to be driven by crystallization of amorphous ice deep in the nucleus. Amorphous ice is a metastable form that traps volatiles like carbon monoxide. When it transitions to crystalline ice, the trapped gases release suddenly, causing explosive venting. Could Atlas be doing something similar? The problem was timing and location. 29P's outbursts happen far from the Sun, where amorphous ice can persist. Atlas was at perihelion, 1.4 astronomical units, where thermal models expect any amorphous ice to have already crystallized. The crystallization mechanism works for distant cold objects, not for comets that have been heating for months as they approach the Sun. The precedent did not quite fit. Next was Comet 1P Halley, one of the most studied comets in history. Halley showed non-gravitational acceleration that was well measured during its 1986 apparition. But Halley's acceleration was textbook standard, exactly what you would expect from water-driven outgassing on a rotating nucleus. The direction, magnitude, and evolution all matched models. Halley was reassuring in its predictability, not a useful analogue for Atlas's anomalies. Comet 17. Holmes provided another case study. In October 2007, homes brightened by a factor of 500,000 in less than 48 hours, transforming from a faint telescopic object into something visible to the naked eye. The outburst created an enormous, expanding cloud of dust that made Holmes temporarily the largest object in the solar system by apparent diameter. The cause remains debated, possibly a subsurface cavity collapse or an impact by a meteoroid, but the event was clearly catastrophic and singular. Atlas had not shown anything like that level of sudden activity. No massive brightening, no explosive fragmentation, just steady anomalous acceleration and irregular rotation. Researchers also examined split comets, objects that had broken apart under tidal stress or internal pressure. When a comet fragments, the pieces separate and follow slightly different orbits. Measuring the separation velocity tells you about the forces involved. Some split comets showed non-gravitational effects that did not align with expected outgassing patterns because the fragmentation process itself imparted momentum in unpredictable directions. But Atlas showed no evidence of fragmentation, no companion pieces, no debris cloud, no diverging orbital elements. It was intact. The precedent search turned up interesting objects, strange behaviors, unexplained events, but nothing that matched the combination of features Atlas displayed. Anomalous acceleration without proportional visible activity. Yes, Oumuamua had that, but Oumuamua lacked a clear coma. Chaotic rotation. Yes, some tumbling asteroids showed it, but not combined with active outgassing. Magnetic signatures, thermal anomalies, density problems, each individually had some parallel in the archive, but the ensemble had no precedent. The conclusion was uncomfortable. Atlas was not entirely without analogues, but it was without a complete analogue. It sat in a gap in the taxonomy of small solar system bodies, sharing features with multiple classes but belonging fully to none. Whatever Atlas was, it was either a rare natural configuration that had not been observed before, or something that required expanding the category of what natural configurations could exist. The simplest explanation for Atlas's behavior, the one that required no exotic physics and no radical reinterpretation of what comets are, was exotic ice. Not exotic in composition necessarily, but exotic in mixture and distribution. Standard cometry models focus on water ice because water dominates most comets. But the solar system has other volatiles. Carbon monoxide, nitrogen, methane, ammonia, all of these can exist as ices under the right conditions. Each has a different sublimation temperature, a different vapor pressure curve, a different way of responding to solar heating. Carbon monoxide ice, for instance, sublimes at much lower temperatures than water. At the distance where water ice is stable and solid, carbon monoxide is already vaporizing vigorously. If Atlas had substantial carbon monoxide mixed with or beneath its carbon dioxide and water ices, that carbon monoxide could drive activity in ways that do not align with standard water-based models. The gas production would be strong, even when surface temperatures were too low for significant water sublimation. The timing of activity would shift. The venting geometry could change, because carbon monoxide does not need focused solar heating to escape. Nitrogen ice is even more volatile. Observations of Pluto and Triton show nitrogen ice on their surfaces, subliming, and refreezing in seasonal cycles. A comet with buried nitrogen ice could have sudden outbursts when subsurface pockets warm enough to transition from solid to gas. The pressure buildup would create geysers, directional jets, that fire episodically, rather than continuously. This could explain why Atlas's dust plumes did not align with expected outgassing patterns. The visible jets might be eruptions from nitrogen vents rather than steady water-driven sublimation. Methane ice adds another layer. Methane has intermediate volatility between carbon monoxide and water. It could create a subsurface engine where methane vaporizes beneath a water ice crust, builds pressure, and vents through cracks. The force from methane outgassing would not produce as much visible dust as water because methane is less effective at dragging particles. You could have strong thrust from invisible gas, creating acceleration that does not match the brightness of the coma. This multi-volatile model, sometimes called the sublimation engine hypothesis, proposed that Atlas had a layered structure. The surface was a crust of refractory dust and processed organics. Beneath that was a mix of water, carbon dioxide, carbon monoxide, nitrogen, and methane ices in varying proportions. As the object warmed, different ices activated at different depths and times. The interplay created complex outgassing, with multiple components operating simultaneously. The appeal of this model was that every ingredient was natural. Carbon monoxide ice exists in the outer solar system. Nitrogen ice exists on Pluto. Methane exists on Titan and in Kuiper Belt objects. Mixing them together in one object was not radical. It just required that Atlas formed in a region of its parent planetary system, where these volatiles were abundant and could be incorporated during accretion. The challenge was testing it. Detecting carbon monoxide and nitrogen in a cometary coma requires specific infrared wavelengths and high spectral resolution. James Webb could do it in principle, but the lines are faint and easily contaminated by telluric absorption from Earth's atmosphere or by other molecular species. Methane is slightly easier to detect, but still difficult at the low abundances expected. Preliminary searches in the Webb data found tentative hints of carbon monoxide emission, a faint line at 4.7 microns that could be carbon monoxide or could be noise. Nitrogen was not detected, but the upper limits did not rule out significant amounts if the gas was cold and the emission weak. Methane was similarly ambiguous. The sublimation engine model could work. It fit the broad outline of Atlas's behavior. It explained anomalous acceleration through invisible, volatile-rich outgassing. It explained the carbon dioxide dominance if carbon dioxide was just one component of a larger volatile inventory. It explained the delayed activity and irregular timing if subsurface pressure dynamics controlled the venting. But it was still a model, not a measurement. And like every other explanation offered for Atlas, it required assumptions that stretched the data just far enough to feel uncomfortable. Space is not empty. Even in the vast regions between stars, there is matter. Hydrogen atoms float in the interstellar medium at densities of roughly 1 particle per cubic centimeter. Dust grains, tiny fragments of silicates and carbonaceous material, drift in the void at even lower densities. And occasionally, larger objects exist, pebbles and rocks ejected from planetary systems or liberated during stellar formation. If Atlas had been traveling through the galaxy for billions of years, it had crossed unimaginable volumes of space. Could it have hit something? An impact, even a small one, could alter a trajectory. Momentum is conserved. If a meteoroid traveling at different velocity strikes a comet, the collision transfers momentum and changes the comet's path. The effect depends on the mass of the impactor, the relative velocity, and the angle of impact. A grazing collision might impart a sideways push. A head-on collision would slow the object down or speed it up, depending on whether the impactor was overtaking or approaching. The numbers, however, do not cooperate. To produce the observed acceleration of 0.3 to 7 millimeters per second, you need to transfer a specific amount of momentum. Calculate the required impactor mass, assuming typical interstellar collision speeds of tens of kilometers per second, and you get something on the order of thousands to tens of thousands of kilograms. That is not a dust grain. That is a boulder, a small asteroid-sized object. The probability of such a collision is vanishingly small. Interstellar space is genuinely empty on human scales. The density of meter-sized or larger objects between stars is so low that the chance of Atlas encountering one during its multi-billion-year journey is negligible. And even if a collision happened, the chance that it occurred precisely during the few weeks when Atlas was under intensive observation, precisely when the trajectory anomaly was detected, borders on impossible. There is also the question of evidence. Impacts produce debris. When two solid bodies collide at high velocity, material is ejected. If Atlas had been struck by a large meteoroid in mid-October 2025, there should be signatures. A sudden brightening from vaporized material, a dust cloud expanding from the impact site, fragments separating on slightly different orbits. None of these were observed. Ground-based monitoring and Hubble imaging showed no sudden changes in coma morphology around the time the acceleration began. The brightness varied, yes, but in ways consistent with rotational modulation and normal outgassing fluctuations, not with a catastrophic impact. Searches for co-moving debris, small objects traveling near Atlas on similar trajectories, came up empty. A variant of the impact hypothesis proposed a swarm rather than a single large object. Perhaps Atlas passed through a dense region of the interstellar medium, a molecular cloud fragment, or a debris stream left by an ancient supernova. Thousands of small impacts from tiny grains, each individually negligible, could accumulate into a measurable momentum change. But this also has problems. Dense interstellar regions are localized. Atlas would pass through such a region in days or weeks at most. The acceleration would be brief and then cease. The observed anomaly persisted over timescales longer than a swarm encounter would predict. There is one version of the impact scenario that is harder to rule out completely. A collision that happened earlier, months or years before detection, could have imparted a structural change rather than immediate momentum transfer. Perhaps an impact fractured the nucleus, creating new pathways for subsurface gas to escape. The outgassing pattern would change, the thrust vector would shift, and the effect would appear delayed relative to the impact itself. This is plausible in principle, but untestable with available data. You cannot prove an impact did not happen in the past. You can only say that an impact during the observation window is inconsistent with what was seen. The impact deflection hypothesis offered a mechanism, a way for natural processes to alter Atlas's path. But the probabilities and the evidence pointed elsewhere. Comets sometimes fall apart. Tidal stress, thermal cracking, subsurface pressure buildup, rotational instability, all of these can fracture a nucleus and split it into multiple pieces. When this happens, the fragments separate slowly, drifting apart at velocities of meters per second or less. Each piece continues on a slightly different trajectory. Over weeks and months, the separation becomes visible. What was one object becomes two, then sometimes many. Fragment separation can produce anomalous acceleration. When a piece breaks off, conservation of momentum means both fragments recoil. The main body gets pushed in one direction, the fragment in the other. The magnitude of the push depends on the mass ratio and the separation velocity. If a small piece breaks off a large nucleus, the main body's acceleration is modest but measurable. And here is the key point. The acceleration can occur without visible outgassing if the separation is purely mechanical, driven by structural failure rather than gas pressure. Could Atlas have shed a fragment? The timing would fit. Perihelion passage subjects a nucleus to maximum thermal stress. The temperature gradient between sunlit and shadowed regions is steepest. Ice expands and contracts. Cracks propagate. If Atlas was already structurally compromised, perhaps from billions of years of thermal cycling, or from chaotic tumbling, stressing the material unevenly, perihelion could have been the trigger that finally broke something loose. The predicted signature would be a companion object traveling near Atlas on a similar but not identical orbit. The fragment would have its own small coma if it contained volatiles, or it might be inert if it was purely rocky or dust. The separation velocity would be small, so the fragment would stay relatively close to the parent for weeks before gradually diverging. By November 2025, if a fragment had separated in late October, it should have been within a few thousand kilometers of Atlas, possibly detectable with high-resolution imaging. Searches were conducted. Hubble pointed at Atlas multiple times in November, specifically to look for companions. The images were processed to enhance faint objects near the nucleus. Background stars were subtracted. Known asteroids in the field were masked. The detection threshold was pushed as low as the noise allowed. Nothing was found. No co-moving objects. No secondary condensations. No fragments. Ground-based observatories with wide field cameras also searched, covering larger areas around Atlas to catch fragments that might have separated at higher velocity or earlier in time. Automated detection algorithms scanned for anything moving with Atlas's proper motion. Again, nothing. The searches were not exhaustive. A very small fragment, a few meters across, could have escaped detection, but anything large enough to impart the observed acceleration through recoil should have been visible. There is a variant scenario where the fragment does not survive. Perhaps a piece broke off, vented gas vigorously, and then disintegrated completely into dust, too dispersed to detect as a discrete object. The recoil from separation would still affect Atlas's trajectory, but the fragment itself would vanish into the background coma. This is harder to test because the evidence self-destructs. Another variant involves internal rearrangement rather than external separation. Maybe a large void inside the nucleus collapsed. Material shifted from one region to another. The center of mass moved slightly within the object. From the outside, this would look like acceleration, even though no material actually left. But internal rearrangement does not explain the non-gravitational effects unless it changes the outgassing distribution, and there is no clear mechanism for a collapse to preferentially enhance venting in one direction. The fragment separation hypothesis was testable, and it was tested, and it came back negative. Atlas appeared to be intact. Whatever caused the acceleration, it was not a chunk breaking off and drifting away. The object remained whole, anomalous but undivided, accelerating through space for reasons that structural failure could not explain. Sunlight carries momentum. Photons have no mass, but they have energy, and energy in motion exerts pressure. When light from the sun strikes an object, it pushes. The force is tiny, measured in micronewtons for objects the size of spacecraft, but it is real and measurable. Spacecraft engineers have to account for solar radiation pressure when planning missions. Over time, the accumulated push can alter orbits. For small objects with large surface areas, radiation pressure can be significant. A flat reflective sheet, something thin and light with high reflectivity, would experience substantial acceleration from sunlight. This is the principle behind solar sails, proposed propulsion systems that use large reflective membranes to catch solar photons and gradually build velocity. The acceleration is slow, fractions of a millimeter per second per day, but it is continuous and requires no fuel. When Oumuamua exhibited non-gravitational acceleration without a visible coma, Avi Loeb and colleagues published a paper exploring whether a light sail could explain the observations. The idea was that if Oumuamua had a high area-to-mass ratio, if it was shaped like a thin disk or sheet rather than a compact sphere, radiation pressure could produce the observed acceleration. The shape required was extreme, something like a pancake only tens of meters thick, but hundreds of meters wide, or a cigar with similar proportions. Natural processes do not typically create such geometries, which is why the proposal attracted attention and controversy. Could radiation pressure explain Atlas? The first step is calculating the required area-to-mass ratio. The observed acceleration is around 0.3 to 7 millimeters per second. Solar radiation pressure at 1.4 astronomical units provides a force of roughly 9 micronewtons per square meter for a perfectly reflective surface. To get the observed acceleration, you need a specific ratio of surface area catching photons to total mass-resisting acceleration. The math gives you an area-to-mass ratio that depends on assumptions about reflectivity and orientation. For a highly reflective surface, always perpendicular to sunlight, the required ratio is achievable if Atlas has large flat regions and low density. But here is the problem. The density issue raised earlier already suggested Atlas might be implausibly light if the size estimates are correct. Adding the requirement for high reflectivity and specific geometry makes the scenario even more constrained. Observational data push against the light sail hypothesis. Atlas's color is reddish, not the bright reflective white or silver you would expect from a highly reflective surface. The polarization signature indicates dusty, organic-rich grains, not clean metal or ice. Spectroscopy shows absorption features from silicates and carbon compounds, materials with low albedo. None of this fits a reflective sail. Additionally, radiation pressure acceleration has a predictable direction. It points radially away from the sun. As the object moves in its orbit, the direction of radiation pressure changes smoothly, always aligned with the sun-object line. Atlas's acceleration vector did not align purely radially. It had transverse and oblique components that radiation pressure alone cannot produce unless the object is tumbling in a very specific way or has asymmetric reflective patches. The tumbling could theoretically help. If Atlas was shaped like a disk and tumbling chaotically, different faces would catch sunlight at different times, creating a time-averaged force that is not purely radial. Modeling this requires knowing the exact shape, rotation state, and surface reflectivity distribution. Without resolved imaging, the models are under-constrained. The radiation pressure sail hypothesis worked for Oumuamua, as a speculative explanation, because Oumuamua lacked a coma and had unusual shape constraints from its light curve. For Atlas, with an active coma, dusty polarization, and reddish color, the hypothesis fits poorly. It requires assuming the object has properties contradicted by multiple independent observations. Radiation pressure contributes to Atlas's dynamics. Yes, all objects in the solar system experience it, but it does not appear to be the dominant or anomalous force driving the trajectory change. Objects are not always solid monoliths. Many small bodies in the solar system are rubble piles, collections of fragments held together by weak gravity rather than structural strength. Inside these objects, voids exist, empty spaces between boulders, gaps filled with fine dust, and in the case of icy bodies, reservoirs of liquid or gas trapped beneath the surface. When conditions change, when heating penetrates or pressure builds, the interior can shift. Internal reorganization is a process where mass moves inside an object without leaving it. Imagine a hollow sphere partially filled with water. If you rotate the sphere, the water sloshes around. The center of mass shifts. From the outside, measuring only the sphere's position and motion, this would look like the sphere is accelerating, even though no external force is acting and no mass is escaping. The movement is internal, but the effect is external. For Atlas, internal reorganization could work like this. Subsurface ice melts as solar heating penetrates deeper into the nucleus. Liquid water, or vaporized carbon dioxide, collects in pockets and cavities. As the object rotates, these fluids shift under the influence of centrifugal effects and pressure gradients. The redistribution of mass changes the moment of inertia. It alters the balance of forces, and if the shifting is asymmetric, if more mass moves to one side than the other, the center of mass migrates, and the object's trajectory responds. This mechanism has precedent in spacecraft dynamics. Satellites with liquid fuel experience slosh, oscillations of fuel inside tanks that can destabilize the spacecraft's orientation or subtly alter its orbit. Engineers design baffles and bladders to minimize slosh because uncontrolled fluid motion is a source of unpredictable behavior. A natural object like Atlas would have no baffles, no control. If subsurface fluids existed, they would slosh freely. The appeal of this hypothesis is that it requires no external forces and no loss of material. The acceleration comes purely from internal rearrangement. It could explain why the outgassing visible in the coma does not align with the trajectory change. The gas we see might be surface venting, while the acceleration is driven by invisible internal dynamics. Testing this idea requires knowing whether Atlas has subsurface liquids or mobile gas pockets. Direct evidence would be difficult to obtain without seismic measurements or ground-penetrating radar, neither of which are possible for a distant interstellar object. Indirect evidence might come from changes in rotation state. If mass is shifting inside, the rotation period and axis orientation should evolve in measurable ways. The chaotic tumbling observed in light curves could be consistent with internal mass redistribution, though it could also result from other causes, like asymmetric outgassing or tidal perturbations. There is a thermodynamic problem. Melting ice or vaporizing carbon dioxide requires heat. At one point, 4 astronomical units, sunlight provides enough energy to sublimate surface ices, but penetrating deep enough to melt interior reservoirs takes time. Thermal models suggest that heat diffuses into a comet nucleus slowly, centimeters per day at most. For internal melting to drive reorganization on the timescales observed, weeks to months, the heating would need to reach depths of meters. That is plausible if the nucleus has high thermal conductivity, or if cracks and fissures allow heat to penetrate faster than diffusion alone. Another issue is reversibility. If mass shifts internally, why does the acceleration persist? Once the fluids settle into a new equilibrium, the center of mass should stabilize, and the apparent acceleration should stop. A sustained effect requires continuous reorganization, fluid constantly moving rather than reaching steady state. This could happen if heating is ongoing and creating new pockets of liquid or gas, but it requires specific thermal and structural conditions. The internal reorganization model is physically plausible. It invokes processes known to occur in icy bodies and spacecraft. But like other natural explanations for Atlas, it is under-constrained by observations. The hypothesis explains some features, conflicts with none definitively, but lacks direct confirming evidence. It remains a possibility, one more entry in the growing list of maybes. Tidal forces are subtle but powerful. When an object passes close to a massive body, the gravitational pull is stronger on the near side than the far side. This differential force, the tidal force, stretches the object. For solid rocky bodies, the effect is negligible unless the approach is extremely close. But for loosely bound rubble piles or structurally weak objects, tidal stress can crack, deform, or even completely disrupt the body. Atlas passed perihelion at 1.4 astronomical units from the Sun in late October 2025. At that distance, solar tidal forces are weak compared to what a comet experiences during a close sun-grazing pass, but they are not zero. If Atlas had pre-existing fractures, zones of weakness from billions of years of thermal cycling and mechanical stress, the tidal pull at perihelion could have been enough to widen cracks, shift internal blocks, or trigger delayed structural failures. The key word is delayed. Tidal stress peaks at closest approach, but the response of the material is not instantaneous. Rock and ice have elastic properties. They deform under stress and then relax when the stress is removed. In some materials, especially those with complex internal structures like layered ice and dust, the relaxation is not immediate. Stress can propagate through the body over hours, days, or even weeks, causing fractures to open progressively rather than all at once. This delayed response mechanism is called tidal resurrection, a term borrowed from studies of short-period comets that show renewed activity weeks after perihelion. The idea is that tidal stress during perihelion creates damage that manifests later. Cracks open slowly, subsurface voids collapse in stages, sealed pockets of volatile ices become exposed to sunlight and begin venting. The activity ramps up, not at perihelion, but afterward, once the damage has fully propagated. For Atlas, the timeline fits loosely. Perihelion occurred in late October. The acceleration anomaly became detectable in mid-October, roughly 3 weeks after closest approach. 3 weeks is a plausible timescale for delayed tidal effects if the nucleus has a complex structure with slow crack propagation. The acceleration could result from newly opened vents releasing gas in directions that were previously blocked by intact surface layers. The problem with this scenario is magnitude. Solar tidal forces at 1.4 astronomical units are small. Calculating the tidal stress on a 5-kilometer object at that distance gives values well below the tensile strength of most ices and rocks. To fracture material, the stress needs to exceed the strength. For weak, porous structures, or for material already on the verge of failure, small additional stress might be enough to tip the balance. But this requires the nucleus to be in a very specific pre-stressed state. Evidence for tidal damage would include visible changes in the nucleus shape or surface features. If cracks opened or chunks shifted, high-resolution imaging might detect them. Hubble's images of Atlas did not show obvious fragmentation or major structural changes between pre-perihelion and post-perihelion observations. But the spatial resolution was limited. Subtle changes, meter-scale cracks, or small displaced blocks would not be visible. Another signature would be correlation between tidal stress direction and outgassing direction. Tidal forces have a geometric pattern, strongest along the line connecting the object to the Sun and weakest perpendicular to it. If venting preferentially occurred along tidal stress lines, that would support the hypothesis. The dust plumes observed by Hubble did not show clear alignment with expected tidal geometry. But again, limited data makes definitive conclusions difficult. Tidal resurrection offers a natural mechanism for delayed activity and structural change. It fits the timing and does not require exotic materials or processes. But the forces involved seem too weak unless Atlas was extraordinarily fragile, and the observational evidence for tidal damage is ambiguous at best. Like many explanations proposed for Atlas, it is plausible in the abstract, but difficult to confirm or rule out with available data. Magnetic fields and charged particles interact in ways that can produce forces. This is the principle behind electric motors, particle accelerators, and the aurora. In space, magnetic interactions are everywhere. The solar wind carries the sun's magnetic field outward through the solar system. Planets with magnetic fields deflect the solar wind, creating magnetospheres. Charged dust grains align with magnetic field lines. And, in rare cases, objects with their own magnetic properties can experience torques and forces when they move through magnetized plasma. Could Atlas have magnetic properties? Most comets are thought to be magnetically inert. They are collections of ice, dust, and rock with no significant iron content and no mechanisms for generating magnetic fields. But not all materials are non-magnetic. Meteorites contain iron-nickel grains. Some asteroids, particularly those from differentiated parent bodies that once had molten cores, carry remnant magnetization from ancient magnetic fields. If Atlas formed in a planetary system around a star with a strong magnetic field, or if it incorporated material from a magnetized environment, it could in principle contain ferromagnetic inclusions. A magnetized object moving through the solar wind would experience magnetic torques. The interaction depends on the object's magnetic moment, the strength and orientation of its internal field, and the configuration of the interplanetary magnetic field it is passing through. The torques could alter the rotation state, causing the object to spin up or down or precess in specific ways. They could also, under certain conditions, produce translational forces if the magnetic field is non-uniform. The force from magnetic interaction is generally small compared to gravitational or outgassing forces. But for a low-mass object with strong magnetization, moving through regions where the interplanetary magnetic field has sharp gradients, the effect could be measurable. The solar wind is not uniform. It has structure, streams, and shocks. Coronal mass ejections create temporary enhancements in field strength. If Atlas passed through such a region while magnetized, the interaction could produce transient acceleration. Testing this hypothesis requires knowing whether Atlas is magnetic. Direct measurement would require a spacecraft with a magnetometer passing close by, which is not happening. Indirect evidence might come from the solar orbiter detection discussed earlier. The localized magnetic disturbance observed during the distant flyby could have been an induced effect from ionized coma gas, or it could have been interaction with an intrinsic field. Distinguishing between these possibilities requires detailed modeling of plasma physics around the object, modeling that depends on knowing the gas density, ionization fraction, and field geometry, none of which are well constrained. Another test involves the rotation state. Magnetic torques exert preferential forces depending on orientation. If Atlas's chaotic tumbling was being influenced by magnetic interaction with the solar wind, the tumbling should show correlations with solar wind conditions. When the interplanetary magnetic field is strong or oriented in specific directions, the rotation rate or axis might change measurably. No such correlations have been reported, but the light curve data is sparse, and the solar wind monitoring at Atlas's location is limited. There is also a compositional argument. Spectroscopy of the coma showed silicates and carbon compounds, but no strong signatures of metallic iron. Iron has distinct spectral features in the ultraviolet and near-infrared. Their absence suggests iron is either not present in significant amounts, or is locked in forms that do not produce detectable lines, such as embedded in silicate grains or oxidized into rust. The magnetic torque hypothesis is exotic. It requires Atlas to have properties not observed in typical comets, and to be interacting with the solar environment in ways rarely considered. It is not impossible. Magnetic interactions happen throughout the solar system, but it is a low probability explanation given the lack of direct evidence for magnetization and the weakness of the expected forces. Like radiation pressure and internal reorganization, it is a mechanism that exists in nature but does not obviously fit the observations of Atlas. Every trajectory goes somewhere. When an object changes course, intentionally or not, its future path shifts. For Atlas, the post-perihelion acceleration altered the orbital elements in ways that could be projected forward. Where was Atlas heading now? Was the new trajectory meaningfully different from the old one? And if so, in what way? Orbital mechanics allows precise prediction over short timescales. Calculate the current position and velocity, apply the gravitational forces from the Sun and planets, integrate forward, and you get a future path. For Atlas, the pre-acceleration trajectory had been well established. The object was on a hyperbolic orbit, inbound velocity of 58 kilometers per second relative to the Sun, outbound at nearly the same speed after the gravitational slingshot around perihelion. The path was simple, a smooth hyperbola that would carry Atlas back out of the solar system and into interstellar space. The post-acceleration trajectory differed by small but measurable amounts. The outbound velocity changed slightly. The direction shifted by a fraction of a degree. Over distances measured in astronomical units, these changes were minor. Over distances measured in parsecs and thousands of years, they accumulated into something noticeable. Researchers ran the projections. If the acceleration observed in October 2025 represented a permanent change rather than a transient effect, where would Atlas be in 10,000 years? in 1 million years. The calculations placed Atlas on a galactic trajectory that diverged from the original path. The new heading pointed toward a region of the local stellar neighborhood, slightly offset from where the old trajectory would have taken it. What made this interesting was not the destination itself. There is no specific star or landmark at that location, but the nature of the correction. The change in trajectory was not random. It was not aligned purely with solar heating geometry or solar radiation pressure. It had components that, when translated into galactic coordinates, looked vaguely like a navigational adjustment. As if the object had been on one path, measured its position, and made a small correction to aim slightly differently. This is where interpretation becomes speculative. You can describe the trajectory change in purely kinematic terms, a delta V vector applied at a specific time resulting in a new orbital solution. That is objective. But when you start asking whether the change is optimized for some purpose, you are importing assumptions. Optimized relative to what goal? Reaching a specific star? Avoiding a specific region? Maintaining a particular galactic longitude? Without knowing the objective function, you cannot determine whether a trajectory is optimized. Statistical tests can ask whether the new trajectory is more or less likely to intersect interesting objects or regions. Does it pass closer to nearby stars than the old path? Does it align with known stellar streams or moving groups? Does it point toward regions of recent star formation or high stellar density? Preliminary analyses found no strong correlations. The new trajectory was not obviously aimed at anything in particular, at least not in the catalogues of stars and structures within a few hundred parsecs. One subtle detail emerged from the galactic coordinate analysis. The acceleration vector had a small component aligned with the direction of the local standard of rest, the average motion of stars in the solar neighborhood. If sustained over time, this component would slightly increase Atlas's velocity relative to the LSR. Whether this was coincidental or meaningful depended entirely on whether you believed the acceleration was controlled. For researchers committed to natural explanations, the trajectory change was an outcome of physical processes, outgassing or structural shifts, or some combination, and any apparent optimization was pareidolia, seeing patterns in noise. For those entertaining alternative hypotheses, the trajectory change looked less random and more deliberate than chance alone would predict. The numbers were the same. The interpretation diverged. Atlas was heading somewhere new. Whether that somewhere mattered, whether the course change served a function, or was simply the result of forces acting without intent, remained an open question. The object would reach its new destination in millennia, long after everyone currently observing it had turned to dust. The trajectory was real. The purpose, if any, was unknowable. Numbers sometimes line up in ways that make you pause. The acceleration of Atlas became detectable starting around October 15th, 2025, based on astrometric measurements that showed consistent deviations from the predicted orbit. Perihelion, the closest approach to the Sun, occurred on October the 29th. The time between these two dates is approximately 14 days, but more careful analysis of the orbital fits, accounting for when the acceleration actually began rather than when it became statistically significant, pushed the start date earlier to around October 4th or 5th. October 4th to October the 29th is 25 days. Some analyses place the onset closer to September 27th, making it 32 days. The range spanned roughly 1 to 5 weeks before perihelion, settling around 3 weeks. But another number kept appearing. When researchers calculated the time from perihelion to the midpoint of the acceleration event, the moment when the accumulated velocity change was half its total value, the number came out to 47.3 days. Different teams using different software got 46.8, 47.1, 48.2. The values clustered tightly around 47 days. 47 is not special in orbital mechanics. It is not a resonance period. It does not match Atlas's irregular rotation or any planetary cycle. It is just 47 days, a number with no obvious significance. This is where pattern recognition becomes a liability. Search hard enough through complex data, and you will find numerical coincidences. There is no reason it could not have been 32 or 63 days. The fact that it came out near 47 proves only that time passed and someone counted. But the tightness bothered some researchers. If acceleration was driven by random outgassing or chaotic processes, the timing should be sloppy. Different datasets should give wildly different answers. Instead, the timing appeared crisp. The acceleration turned on over a narrow window and reached a plateau that multiple teams independently pegged near 47 days post-perihelion. Statistical tests asked what probability purely random cometary activity would produce such consistent timing. The answer depended on assumptions. If outgassing is random, the probability of tight timing is low. If thermally driven with predictable lag times, the probability is higher. One researcher noted that 47 days is roughly 1/16 of a Martian year. Another pointed out it equals 7 weeks, a human division with no astronomical relevance. A third calculated it equals the light travel time across 8 astronomical units. Numerically interesting, but physically meaningless here. The timing might mean nothing. It might be thermal processes, reaching a threshold after perihelion heating penetrated deep enough. Or it might be precise in ways natural stochastic processes rarely are. The coincidence was noted, catalogued, and filed alongside other anomalies. If there was even remote possibility Atlas was not entirely natural, someone had to ask, should we try communicating with it? And who decides what to send? SETI has protocols for this. Decades of discussion produced guidelines emphasizing caution. No response should be sent without international consultation. The content must be carefully considered. Replying carries risks transcending national boundaries. But Atlas was not a radio signal. It was a physical object passing through the solar system, not broadcasting in any detected wavelengths. If it was a probe, it was silent. And silence presents a different problem. Do you wait for it to speak first or take initiative? In early November 2025, Breakthrough Listen dedicated observing time on the Green Bank telescope to monitor Atlas across wide radio frequencies. The observations searched for any emissions indicating technology. The monitoring ran 40 hours over 2 weeks. Nothing was found. Atlas was radio silent. Optical SETI also pointed instruments at Atlas, searching for brief laser pulses an advanced civilization might use. Observations were conducted at multiple observatories. Again, nothing. No pulses, no modulation, no optical anomalies beyond reflected sunlight and coma scatter. The absence of signals did not prove Atlas was natural. A probe designed for passive observation would not broadcast. It would listen, record, and remain quiet. Or it might communicate, using methods we do not recognize, gravitational waves, neutrino beams, technologies outside our detection capabilities. Then, the question flipped. Should we send a message to Atlas? Active SETI, also called METI, is controversial. Some argue announcing our presence to unknown intelligences is reckless. Others argue that if an advanced civilization sent probes here, they already know we exist, and attempting communication is reasonable. A coalition drafted a proposed message, including basic mathematics, prime numbers, solar system diagrams, the hydrogen line frequency. The proposal was to transmit using a high-power radio telescope, aiming at Atlas's position, repeating multiple times over days. The proposal stalled. Questions of authority arose. Who has the right to send messages on behalf of humanity? Regulations exist for radio emissions, but not interstellar messaging. The UN Office for Outer Space Affairs provided no clear guidance. Nations claimed jurisdiction, or argued consensus was required. By mid-November, bureaucracy had bogged down. Time was running out. Atlas was moving away daily. If a message was going to be sent, it needed to happen before the object was too far for practical two-way communication. In the end, no official message was transmitted. The silence from Atlas was met with silence from Earth, not by decision, but by indecision, by institutional inability to move quickly, facing unprecedented circumstances. Polarization measurements are exacting work. Early observations in September and October 2025 found that deep, narrow negative polarization branch at negative 2.7%. The feature was unprecedented, unlike anything in solar system comets or Borisov. In late November, as Earth's geometry shifted, new observations were conducted at angles between 25 and 38 degrees. Standard cometary dust shows polarization rising smoothly with phase angle, crossing from negative to positive around 15 to 20 degrees, then climbing steadily. Atlas did not follow the standard curve. Measurements at 25 degrees were lower than expected based on earlier data. At 30 degrees, even more anomalous, sitting well below predicted trend lines. At 38 degrees, the suppression persisted. This was not measurement error. Multiple independent teams, using different telescopes, obtained consistent results. The polarization curve had changed shape. Post-perihelion dust was scattering light differently than pre-perihelion dust. Several explanations were proposed. The dust grain population might have evolved. Early in apparitions, larger grains dominate. As activity continues, finer grains release. Grain size affects polarization, so if Atlas was releasing more small grains, the curve would shift. Another possibility was compositional change. If surface layers venting in September differed chemically from deeper layers venting in November, dust composition might have changed. Organic-rich particles scatter differently than silicate-rich ones. A third idea involved dust processing in the coma itself. After release, grains are exposed to solar radiation and solar wind. Over time, this alters surface chemistry and grain properties. If November's coma contained older, more processed dust, polarization would differ. Each explanation was plausible and natural, but Atlas's polarization shift was larger than typical variations. The curve had not just shifted, but restructured in ways difficult to fit with simple grain size or composition changes. The more exotic interpretation, floated but not published, was that early polarization was anomalous for reasons unrelated to natural dust, and later measurements represented return to typical behavior. If October's deep negative branch resulted from unusual microstructure, perhaps deliberately engineered, the November shift could indicate those grains were no longer produced or had been diluted. This required assumptions far beyond data, but polarization had changed unexpectedly, adding another layer to the mystery. The dust was evolving in ways that did not follow ordinary comet scripts. Science operates on peer review. In late November 2025, multiple ATLAS papers circulated in review stages. One submitted to Nature presented trajectory anomaly data and explored natural explanations. The authors concluded that while mechanisms could partially explain observations, none provided complete accounts. The paper was careful, hedged, technically solid. Reviews came back mixed. 2 reviewers recommended acceptance with minor revisions. A third recommended rejection, arguing the framing left too much interpretive space and would fuel speculation for non-natural hypotheses without sufficient evidence. This was editorial judgment, not scientific. The paper did not claim ATLAS was artificial. It documented that standard models did not fully explain observations. But in the current climate, the line between reporting uncertainty and encouraging speculation felt uncomfortably thin. Nature declined the paper, citing need for more definitive conclusions. The decision sparked controversy. Was Nature protecting rigor or suppressing inconvenient data? Meanwhile, papers appeared on Archive. One argued ATLAS's acceleration was fully explained by asymmetric carbon monoxide outgassing. Another, posted days later, concluded carbon monoxide alone was insufficient. A third explored statistical likelihood of the trajectory being navigational correction, calculating Bayesian probability depending on chosen priors. Social media amplified divisions. Researchers advocating conservative explanations were accused of closed-mindedness. Those entertaining alternatives were accused of sensationalism. The discourse polarized in ways hindering understanding. Senior astronomers tried lowering temperature. Editorials called for patience, urging waiting for more data. But patience is difficult when the object is leaving and the data window is closing. The firestorm was not about science itself. Measurements were not disputed. The controversy was about interpretation, acceptable uncertainty, what counts as reasonable hypothesis, and who decides. These are questions without clear answers, philosophical more than empirical. In the absence of definitive data, the debate continued, loud and unresolved, as ATLAS drifted farther into dark. If ATLAS is controlled, if trajectory change represents deliberate maneuvering, then the object has traveled through the galaxy for billions of years, with guidance systems intact. Kinematic age estimates place ATLAS between 3 and 11 billion years old, based on velocity dispersion and motion, relative to the local standard of rest. Even the conservative bound makes it older than the solar system. Consider what this means. 3 billion years ago, Earth was bacteria and algae. No animals, no plants, nothing complex. Human civilization spans roughly 10,000 years. 3 billion years is 300,000 times longer. If ATLAS has traveled that duration with functional systems, those systems operated across timescales, dwarfing anything humanity has built. Spacecraft do not last billions of years. Voyager probes launched in 1977 are now over 45 years into missions. Power sources are decaying, systems failing. Within decades, they will go silent, dead hulks drifting through interstellar space. The idea of probes functioning for billions of years requires materials and technologies far beyond anything we understand, or fundamentally different approaches to longevity. One concept appearing in theoretical discussions is hibernation. Not biological, but engineered dormancy. A probe designed for eons might spend most of its journey powered down, inert, essentially a rock. Only when encountering something of interest does it activate. Sensors wake, instruments turn on, navigation engages. The probe observes, records, perhaps adjusts trajectory before returning to dormancy. What would trigger activation? Proximity to a star is the simplest criterion. As the probe enters a stellar gravity well, as light and particle flux increase, passive sensors could detect the change and initiate a wake-up sequence. No onboard clock needed, no complex logic, just a threshold crossed and systems come online. Could Atlas have been dormant for billions of years and only recently activated? The timing is suggestive. The object entered the solar system in 2025. Within months of passing perihelion, it exhibited behavior that standard models struggle to explain. If activation is real, the solar heating at perihelion could be the trigger. Not because heat powers the probe directly, but because perihelion represents the moment of closest approach to the Sun, the optimal time for observations and course corrections. This scenario requires assumptions that stack uncomfortably. You need the object to be artificial. You need it to have survived billions of years. You need it to have activation protocols tied to stellar proximity. You need the trajectory change to be intentional. Each assumption is individually speculative. Together, they form a narrative that is imaginative but unsupported by definitive evidence. There is also the question of purpose. Why send probes on billion-year journeys? What civilization plans on timescales that long? Even if a society persists for millions of years, why build something designed to function for billions? One answer is exploration at galactic scale. If you want to survey the entire galaxy, if you want to visit every star system and catalogue every planet, you launch billions of probes and you wait. The probes drift, carried by galactic dynamics, entering stellar systems by chance or by minimal guidance. Over billions of years, statistical coverage becomes comprehensive. Another answer is messaging. The probes are not explorers, but beacons, packages of information distributed across the galaxy waiting to be found. Activation occurs when a technological civilization develops the capability to detect and study interstellar visitors. The probe does something noticeable, a trajectory change, an anomalous signature, enough to provoke investigation. And if the civilization is advanced enough, they retrieve the probe or decode its message. Both scenarios are speculative frameworks, science fiction treated as hypothesis. They fit the observations only if you accept premises that remain unproven. But the deep time aspect is unavoidable. If Atlas is anything other than a natural comet, it has been out there, traveling, waiting, for longer than complex life has existed on Earth. There was a moment in early November 2025 when the possibility of an intercept mission seemed almost within reach. Engineers ran the calculations. The delta V required, the time to design and build a spacecraft, the launch windows, the trajectory options. The numbers were brutal, but not quite impossible. A flyby mission, one that would pass close to Atlas without matching speed, could theoretically be launched within 18 months if every decision was made immediately and every constraint relaxed. The design studies converged on a similar architecture, a small spacecraft, no more than 500 kilograms, built around a compact instrument suite. Cameras for imaging the nucleus at high resolution, a spectrometer for compositional analysis, a magnetometer to detect any intrinsic or induced magnetic fields, a dust analyzer to capture and characterize particles from the coma. Simple, focused, achievable with existing technology. Propulsion was the limiting factor. A direct trajectory to intercept Atlas required enormous velocity. The object was already moving at 58 kilometers per second relative to the Sun and accelerating outward. Catching up meant launching faster than any planetary mission had ever flown. Chemical rockets could not do it. Ion propulsion, efficient but slow, could not build speed quickly enough. The only realistic option was a gravity assist trajectory, using Jupiter or Saturn to slingshot the spacecraft onto an intercept path. Jupiter gravity assists are powerful but infrequent. Planetary alignments that allow efficient transfers happen only during specific windows. The next favorable geometry for a Jupiter assist aimed at Atlas's projected location was in mid-2027, roughly 2 years away. By that time, Atlas would be beyond 6 astronomical units from the Sun and still receding. The intercept could happen, but it would occur far from the Sun, deep in the outer solar system where solar power is weak and communication delays are long. The timeline from approval to launch was the breaking point. Spacecraft missions, even fast-tracked ones, take years. You need to finalize the design, build the hardware, integrate the instruments, test everything in thermal vacuum chambers and vibration tables, write the flight software, and conduct rehearsals. NASA's New Horizons mission to Pluto, considered a rapid development by space agency standards, took about 5 years from approval to launch. Compressing that to 18 months would require cutting corners, skipping redundancy, accepting higher risk. Cost was another barrier. A dedicated interstellar object intercept mission, even a minimal one, would run into hundreds of millions of dollars. Funding for such a mission does not appear overnight. It requires budget proposals, congressional approval in the United States, or equivalent processes in other spacefaring nations, and competition with other priorities. In late 2025, no government had allocated funds for an Atlas mission. Private entities expressed interest, but lacked the infrastructure to execute alone. There was also the question of scientific return versus risk. A flyby at tens of kilometers per second gives you seconds to minutes of close observation, depending on how near you pass. Miss the timing by a small navigational error, and you get nothing. The target is small, a few kilometers across at most, tumbling unpredictably. Hitting a narrow intercept corridor after years of flight is difficult, even for well-characterized targets. For an object whose trajectory might still be changing due to outgassing or other effects, the uncertainty is higher. By mid-December 2025, the window for decision had closed. No agency committed to a mission. No funding materialized. Engineers filed their studies in archives labeled "What Could Have Been." The spacecraft that might have revealed Atlas's secrets remained unbuilt, a collection of diagrams and spreadsheets gathering digital dust. Humanity had discovered an interstellar visitor exhibiting behavior that defied easy explanation, and the response was to watch it leave. Not because we lacked the capability, but because we lacked the will, the coordination, and the speed to act before the opportunity vanished. In 2027, when the launch window arrived, Atlas would be too far, moving too fast, already beyond reach. The mission we are not flying will be remembered as the chance we did not take. Atlas is the third confirmed interstellar object to pass through our solar system. Oumuamua arrived in 2017. Borisov followed in 2019. Atlas appeared in 2025. 3 objects in 8 years. The sample size is small, but it is growing, and the rate of discovery is accelerating as surveys improve and telescopes become more sensitive. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, began operations in 2024. Its mission is to survey the entire visible sky every few nights, going deep, detecting faint objects that previous surveys would miss. Rubin's wide-field camera and rapid cadence make it exceptionally good at finding things that move: asteroids, comets, and crucially, interstellar visitors. Estimates suggest that Rubin could detect between 50 and 200 interstellar objects per year once it reaches full survey mode. These are not precise numbers. They depend on assumptions about the size distribution of interstellar objects, their velocities, their albedos, and how many of them pass through the inner solar system at any given time. But even the conservative estimates predict that within a decade, we will have catalogued hundreds of interstellar visitors. The era of interstellar objects, being rare curiosities, is ending. The era of statistical samples is beginning. What happens when we have hundreds of examples? We can start answering questions that 3 objects cannot resolve. How common are carbon dioxide-rich comets versus water-rich ones? What fraction show non-gravitational acceleration? What is the distribution of rotation? States, sizes, colors, trajectories? Do interstellar objects cluster in certain regions of the sky, suggesting they come from specific stellar populations or moving groups? Or are they distributed uniformly, consistent with a well-mixed galactic background? And here is the question that makes people uncomfortable. What fraction of interstellar objects exhibit anomalies? If 1% of the objects Rubin finds show behavior like Atlas, trajectory changes that do not fit standard models, polarization signatures unlike anything seen before, timing coincidences and compositional oddities, then we are looking at 1 or 2 anomalous objects per year. Over a decade, that is 10 to 20. Over a century, hundreds. At what point does anomalous become a category rather than an exception? If every 50th interstellar visitor does something strange, something that resists natural explanation, despite extensive analysis, do we continue invoking increasingly elaborate natural mechanisms for each one? Or do we start considering that some small fraction of these objects might be something else? This is not an argument for jumping to conclusions. It is an argument for preparation. If the null hypothesis that all interstellar objects are natural starts accumulating enough exceptions that it becomes statistically strained, the scientific community needs to have frameworks in place for evaluating alternatives. That means defining what evidence would be sufficient to warrant serious consideration of non-natural origins. It means establishing protocols for investigation, observation priorities, data sharing, and communication. The multiplicity question also has a flip side. If Rubin finds hundreds of interstellar objects and none of them show the anomalies Atlas exhibits, that would be informative. It would suggest Atlas is a rare outlier, perhaps a 1 in 1,000 event, where unusual but entirely natural conditions aligned. The strangeness would remain, but the statistical context would shift. Atlas would be weird, but not representative. Conversely, if many objects show similar features, if carbon dioxide dominance and oblique accelerations and unexplained timing become common, then our models of what interstellar objects are and how they behave need updating. The baseline assumptions, drawn largely from solar system comets, may not apply to the broader galactic population. We are living through the transition from anecdote to statistics. 3 objects are anecdotes. 300 objects are a dataset, and datasets reveal patterns that single cases obscure. Whether those patterns point toward a universe full of strange but natural comets, or towards something more unsettling, will become clearer as the catalogue grows. Atlas will not be the last mystery. It may be the first of many, or it may be an isolated anomaly that history remembers as the object that made us question everything before the data proved us wrong. The last scheduled observations of Atlas are planned for March 2026. By then, the object will be beyond 4 astronomical units from the Sun, roughly the distance of Jupiter's orbit, and fading rapidly. The coma will have dimmed as activity declines with increasing distance from solar heating. The nucleus, already barely detectable beneath the veil of gas and dust, will become indistinguishable from background stars. Telescopes will track it as long as photons allow, but eventually the signal will drop below the noise, and Atlas will vanish from our instruments. Where it goes after that is calculable but unobservable. The trajectory, altered by the October acceleration, carries Atlas back into interstellar space on a path slightly different from the one it arrived on. In 10,000 years, it will be light years away, a cold, dark speck drifting through the void between stars. In 1,000,000 years, it will have crossed parsecs, perhaps passing near other stellar systems, perhaps not. In 1,000,000,000 years, if it survives that long without collision or disruption, it will have traversed significant fractions of the galactic disk. We will never see it again. No follow-up mission will catch it. No future telescope will resolve it. The data we have, the spectra and images and measurements collected between July 2025 and March 2026, are all we will ever have. The questions Atlas raised about its origin, its composition, its behavior, will persist long after the object itself has faded into the unreachable distance. Some questions do not get answered. They get inherited. The next generation of astronomers will have better telescopes, larger surveys, more interstellar objects to study. They will compare Atlas to the new arrivals and perhaps see patterns we cannot. Or perhaps Atlas will remain singular, an anomaly that stood alone, refusing to fit any framework we built to contain it. The infinite question mark is not a failure of science. It is a reminder that the universe does not owe us answers on our timescale. Atlas came, changed course, and left. What it was, why it behaved as it did, where it came from, and where it is going, remain mysteries written in the dark, waiting for instruments and minds not yet built to read them.